Hey guys, welcome back to chapter 3. We're going to talk about our next periodic trend, and that is something called ionization energy. And again, this is a trend that is dictated by the electrons. So first, let's define what ionization energy is. Then we'll look at how it trends on the periodic table. So ionization energy is the energy required to remove 1 mole of electrons. So to kind of simplify this, that's a little out there, right? To kind of simplify this, we're going to think about this as removing an electron. So how readily can we take off an electron from one of these atoms? How hard is it holding on to it? How easily is it giving it away? So something that is I'm fine with getting rid of an electron, is going to have a very low ionization energy. So with the ionization energy being low, it does not take a lot of energy to remove that electron. So low ionization energy, fairly easy to take that electron away. Something that has a high ionization energy is going to be holding on to that electron very, very tightly. So the more affinity or the more that atom wants to keep the electron, the harder it is going to be to remove it, which would result in a higher ionization energy. So high ionization energy, really hard to take that electron away. We're going to look at trends again from left to right. We're also going to look at trends from top to bottom. So same idea as we did before. So again, the trend from top to bottom is the easiest to understand. So if we go down that first column here, just like we did right here, we see that hydrogen at the top has a very, very high ionization energy, but more importantly, as we move down the column, we see that the ionization energy decreases. In other words, it's easier to take an electron away as we move from the top to the bottom. Why would that be? Well, think about it this way. The electrons in the valence shell, that outermost shell, as we move down the periodic table, those valence electrons get further and further away from the nucleus. So when they're very close to the nucleus for lithium and sodium, that positively charged proton can hold on to those valence electrons and say, wait, I'm not ready to give this up. But as we keep moving down the periodic table, so for cesium here, we're in the 1, 2, 3, 4, 5, 6th energy level. Now that valence electron is so far away from the nucleus that electron is a lot more susceptible to outside influence, and it's a little bit easier to take that electron away. Okay. The silly analogy that I like to think about here, I've got 2 boys, right? So when they were toddlers, I like to keep them very, very close to me. So I like to keep them a foot or 2 away from me because I have a lot of control over them at that point. I can reach out and kind of grab them, make sure they're safe, prevent them from running in front of a car, something like that. So very close to me, I have a lot of control over their behavior. As they get further and further away from me, so 3 feet away, 4 feet away, 5 feet away, they're a lot more susceptible to outside influence. I don't have as much control on them. And when they're far away, it's a lot harder to reach out and grab them if I needed to grab them. So same thing with the electrons here. Close to the nucleus, a lot more control. Hold on to electron a little bit tighter. Further away from the nucleus, a lot more susceptible to outside influence. Not as easy to hold on to it. We give it up a little bit easier. So top to bottom, ionization energy decreases. As we move left to right, overall, right? So there are some exceptions in here. But generally, as we move from left to right, the ionization energy increases. So over here on the left-hand side of the periodic table, pretty low. Over here on the right-hand side of the periodic table, pretty high. So why would that be? So when we're thinking about these elements, okay? These guys right here next to the noble gases, so fluorine, chlorine, bromine. These guys have 7 valence electrons. They want 8. So 8 is how many our noble gases have. They're very close to being like to 8, right? They just have to get 1. So they're not going to readily give up their valence electrons because they are so close to being like the noble gases. Noble gases are happy with their 8 electrons. They don't want to give them away. So the noble gases and the halogens have very high ionization energies because they are happy with what they have, or for the halogens, they're actually trying to steal one from somebody else. They're not going to give up the ones that they have. So very high ionization energy over on that side of the periodic table. Over here in our alkali metals, alkaline earth metals. As it turns out, these guys have 1 and 2 valence electrons. They actually are okay with giving up or letting somebody take those 1 or 2 valence electrons. Because if somebody takes those 1 or 2 valence electrons, now that energy level is empty, we go down, and that energy level is full. So they're like, you know what? Take my 1 valence electron. Now I don't have to worry about that energy level being almost empty. It's completely empty. And now the energy level below it has 8 valence electrons. It's full. So these guys are actually kind of okay with somebody taking their valence electrons. So they're going to put up much less of a fight. They're going to be like, you know what? Fine, take it. Not a big deal. As opposed to these guys over here that are like, no. You cannot touch my electrons. I'm actually trying to steal them from somebody else, and I'm not going to give up the ones that I have. So that's why the ionization energy increases as we go left to right. There's some kind of interesting oddities on this periodic table. So number 1, we see hydrogen here, right? So like kind of low, kind of low, kind of low. Holy moly, that's huge, right? So let's think about hydrogen. How many electrons does hydrogen have? He's got 1. Only 1 electron, right? So if he loses that electron, what's left? Nothing. So it turns out that hydrogen actually does hold on to his 1 single electron pretty hard. He doesn't want to be left with absolutely no electrons. So that's why hydrogen's electronegativity is a little bit higher than would be expected for this group. Same thing with beryllium here. He's got 2 valence electrons. He only has 2 electrons, period. So that's why he's a little bit higher than like the trend. Another oddity over here happens right here. So I said left to right. Generally, the ionization energy goes up. But look what happens right here between nitrogen and oxygen. There's this little like whoop dip. If we look at the orbital diagrams, we can actually explain what the cause of that dip would be. So here's the orbital diagrams for nitrogen, and here's the orbital diagram for oxygen. So these are the valence electrons. These are the last final electrons that we're putting into the configuration. So we did 1s2, 2s2, now we're filling the 2p. So for nitrogen, to fill the 2p, we would have 1, 1, 1. We run out of electrons. That's it. That's the orbital diagram. Oxygen, we have 1 other extra electron, so we'd go 1, 1, 1, and then pair this up 2. So this electron right here, remember these are both negatively charged particles. They're residing in that same orbital, that same kind of living space, and they're going to be repelled by one another. So it turns out that it's actually a little bit easier to take this paired electron than it would be to take this unpaired electron. This unpaired electron is kind of like, you know what, I'm good just hanging out here. Where these two paired electrons, there is a little bit of repulsion. There is a little bit of kind of pushing away from each other. So it's a little bit easier to take this electron than it is to take an unpaired electron. So that's this little like boop right here. Easier to take our paired electron than it is to take the unpaired. So that's why we see that little dip. I'm not going to ask you guys about the exceptions to the rule. I just think it's kind of fun to apply some of the knowledge that we have. Generally, what you're going to need to know is from top to bottom, the ionization energy decreases. From left to right, the ionization energy increases. And then I would ask a question very similar to what we looked at before. Put them in decreasing order, increasing order. Or I may give you like 4 atoms and say which has the highest ionization energy. So that would be the way that you would approach these problems. I hope you guys found this helpful.